Okay, so let's go ahead and get started. So I'm gonna do a little something different today. So what's gonna happen is that since Kaltura is having issues, like the video from Monday just got uploaded this morning. So I'm gonna try and compensate for that by trying to use a third-party recording software called OBS Studio. Sorry. So to make sure it gets recorded, I'm going to use OBS Studio on this section, if that's okay with you guys. Does anyone not want that to happen? Okay. So a few things before we get started. I'll just put it on the back here, so that way I have it somewhere. So just announcements. Quiz 1. The window for that is 9 a.m. On Wednesday the 2nd, which is today, so in about 30 minutes, to 9 a.m. on the 3rd, so tomorrow. Quiz 2. I got some information about that yesterday since I'm going to be writing that quiz, so basically, it's going to cover lessons 4, 5, and 6. It'll be sometime next week. Okay, sometime next week. And because Kaltura was still having issues Monday and Tuesday, homework 4 got pushed to Thursday at 11 p.m. So just so you guys are aware of that. Okay, so any questions on any of that before we start the lesson? Okay. So let's go ahead and start with lesson 5 on, which formally introduces continuity, even though I've been doing that since, last Friday, but now we're formally talking about it. Formally. Like, talking about it for the first time, quote unquote. So, for the third lesson in a row, let's start by talking about the definition of continuity. Again. Alright. So, recall, we have that a function f of x is continuous at x equals c if 3 things occur. So f of c is defined. F of c is defined. The limit as x approaches c of f of x exists. And then the last thing, and perhaps most importantly, limit as x approaches c of f of x equals f of c. So, as we mentioned on last Friday, one way to intuitively think about the notion of continuity is to say, okay, can I draw the graph of f of x around c without having to pick up my pencil at all? So, can I draw graph around c without picking up pencil? Okay. So that's basically the idea behind continuity. So now on Friday we discussed the idea of how to find discontinuities for a graph of a function. So now let's see how to do so for an explicit expression for a function, whether it be piecewise or not. So to start off with non-piecewise functions, so this is going to be a bit of a long explanation. So take domain into account Okay, so that's basically the sort of the short version of that. So take domain into account. So some functions, such as e to the x, sine of x, cosine of x, and polynomials, are continuous everywhere, but others, like rational functions, logarithms, and the other remaining trigonometric functions, are only continuous on their domains. And remember, this CTS abbreviation is what I'm using to denote the shorthand version of continuous in this class. So just so you guys are aware of that. So for piecewise functions, so check where the pieces of your piecewise function meet up. Because f of x is possibly discontinuous there. Okay. And so the other part is that also check each piece is continuous on its own. Now the nice thing is that part B, you don't have to worry about that too much because usually the pieces by themselves are continuous on the homework. So the good news is you don't have to worry about that too much here, but it's good to just do that just for a quick sanity check. Okay? So, types of discontinuity at C. So, again, we kind of talked about this on Friday, but we'll go ahead and reiterate those concepts here. So, the first one I'm going to talk about in this section, this lesson, is a jump. So f of x has a jump at x equals c if the one-sided limits, limit as x approaches c from the left of f of x, and the limit as x approaches c from the right of f of x exist and are finite. But the problem is that the limit as x approaches c of f of x as a two-sided limit does not exist. And in this case, it's usually because the one-sided limits do not equal each other. So then, and then 3, limit as x approaches c of f of x is not equal to f of c. So the thing is that technically 1 and 2 already imply 3, because if you have something that does not exist, this limit does not exist, then there's no way it can equal f of c, regardless of whether or not it's defined. So even though 3 is formally part of the definition, the only two you really need to worry about are these two. So just to keep that in mind. So one thing to keep in mind with focusing on a jump analytically is that jumps only occur with piecewise functions. Now, that's not to say other types of discontinuity. That's not to say piecewise functions can only have jumps as their only form of discontinuity. But if you're focusing on a jump, then that can only occur with a piecewise function. So, just something to keep in mind for that. So, let's see. Okay. So then I'll go ahead and give the graphs of what those look like, just to give you an idea of what's happening. So, we already had these last time, but I'll just draw the sketches of them again. So, the idea is that, the situation where f of c is defined as indicated by this filled in dot, or let me do this so that way there's no ambiguity here. Let me get my pen, my colored pen out. Okay, there we go. So this is where f of c is, as indicated by the filled in dot. But the caveat is that the one-sided limits, where x approaches c from the left and x approaches c from the right, they approach two completely different y values. So that's where you have to be a bit careful. And then, in a similar fashion, well, you could also have a situation where the one-sided limits don't agree with each other, but f of c is something completely different. So again, f of c is indicated by the filled in dots. So in both cases here, f of c is defined. But that could also be the case where f of c is just straight up undefined or not there. And that's generally going to look like this. So one-sided limits approach two different y values, and f of c is just not there. So f of c undefined. Okay. Okay, any questions on that? Okay. Zoom out a tad bit. So the next type of discontinuity we're going to talk about is the idea of a hole, or reintroduce it to be more precise. So there's a hole at x equals c if the limit as x approaches c of f of x exists and is finite. So the good news is that in this case, both the one-sided limits agree with each other. But the limit as x approaches c of f of x just does not agree with f of c here. And that could be because either f of c is undefined or f of c is defined and they're just not equal to each other. So in a situation like this, you end up with the left side limit and the right side limit around c are agreeing with each other, but this hole here and the fact that there's no filled-in dot indicate that f of c is undefined, so there's no possible way that the two-sided limit can equal the function value. So, because the function value is undefined. F of c undefined. And then, of course, the second scenario is when f of c is defined, but they just straight up don't equal each other. So, in this case, you have, in this case, the filled-in dot is f of c, but it just doesn't agree with the one-sided limit here. So, f of c defined, but not equal to the two-sided limits. Okay. Okay. So any questions on that? Alright, so then the last one is the vertical asymptote. So there's a vertical asymptote if f of c is undefined And the one-sided limits, approaching from the right, and then approaching from the left, are plus or minus infinity. Let me write that a bit neater. There we go. Okay. And then, as we recall, there's sort of three fundamentally distinct ways we can describe a vertical asymptote. Namely, we have something like this, where we approach positive infinity in one direction and then negative infinity in another direction. Okay, so that's one way. The second way is if we have a vertical asymptote, but both the left side and right side limit approach positive infinity. So that's scenario 2. And then scenario 3 is basically the exact opposite as this one, where instead of both of them going up to positive infinity, they go down to negative infinity. So like this. So basically, those are the three fundamentally different scenarios here for a vertical asymptote. Okay. So if you recall from lesson 3, not only do we talk about how to find the limit and function values given a graph, but we also talked about what kind of discontinuities we can get from each of those scenarios. So because of that, there are going to be some homework problems where they'll ask you to, find the discontinuities given a graph. But since we kind of already talked about that in good enough, insufficient detail on Friday, I'm just going to say that we already did that in lesson 3. So for those problems on the homework, I will refer you to lesson 3 notes. So already classified discontinuities from a graph in lesson 3. So now we will classify discontinuities analytically. Okay? So the first example I want to talk about of that is this rational function here. So for example 1, we need to figure out where f of x is discontinuous, if anywhere, and we need to classify those discontinuities. So for this first example here, we have this rational function. So in this case, the only way we can get any type of discontinuity in this case is that we have to focus on where the function itself is undefined. So if you recall, for a rational function, when's the only time we can ever have a undefined function value?
When the denominator is 0.
Right, when the denominator is 0. So if that's the case, for rational functions, we need to set the denominator equal to 0 to get discontinuities. As f of x is undefined when denominator equals 0. Okay? So if that's the case, let's go ahead and take our denominator and set it equal to 0 to get our x values at which there are discontinuities. So we have x squared plus 4x minus 5. So if we factor that, we end up with what two things?
X minus 1 and x plus 5.
Minus 1 and plus 5. Good. Okay? So if we set that equal to 0, then we should end up with the two x values at which there are discontinuities are 1 and -5. 1 and -5. So if you were just asked to give us where there are discontinuities, this would be your answer and you'd be done. Unfortunately, we're not quite done yet, because now we need to classify these discontinuities as well. So, now classify. Okay? So before we do that, let's say, okay, well, if as long as x is not equal to 1 or -5, let's see how we can simplify our function f of x here to see if we can figure out what kinds of discontinuities we can get from this. So we have f of x equals, well, let's see. So what we're going to do, as we did in lesson 4, is we're going to factor the numerator and denominator. So we already have the denominator, that's x minus 1 and x plus 5. But what about the numerator? What does that become? I'm just trying to see if I can give someone else a chance. So. Yep. X minus 1 and x plus 4. Okay. So now as long as x is in our domain of f of x, specifically as long as it's not 1 or -5, we can safely cancel out our x minus 1 factors. So we end up with x plus 4 over x plus 5. So this is our simplified f of x for x not equal to 1 or -5. Okay? So if that's the case, let's go ahead and use this simplified version to get our discontinuities here. So for x equals 1, we have, let's go ahead and first figure out, okay, let's go ahead and take our simplified version and see, does this have a whole or a vertical asymptote? So limit as x approaches 1 of f of x. So using this simplified version of f of x, we have the limit as x approaches 1 of f of x is the same thing as the limit of x plus 4 over x plus 5. So, if we just focus on this limit here, what does that equal? We harken back to what we did last time. Go ahead.
5, 6.
Yep, just 5 over 6, right? Because in this case, we just simply get a case 1 limit from last time, so all we have to do is just let x equal 1 for the simplified f of x, and we're good to go. So, if that's the case, that says our two-sided limit exists and is finite. So that implies of the 3 options that we have for a discontinuity, which one do we end up with? We get a whole, right? So we get a whole at x equals 1. Okay? So there's a whole there, so that's not too bad. Now for x equals -5, now let's go ahead and focus on that. So limit as x approaches -5 of f of x is, again, use the simplified version of f of x plus 4 over x minus 5. Or x plus 5, sorry. But wait a minute. What happens here? So if we just we get f of -5, what do we end up with here, though?
0.
Negative 1 over 0, right? Or more precisely, or more generally, a non-zero number divided by 0. But, oh wait a second, if we harken back to what we had from last time, what did we say about this scenario? So if we had a non-zero number over 0, what did we end up with? Go ahead.
Do like the signs of each one and get negative and negative positive.
Right, because the reason for that is because the one-sided limits were either plus or minus infinity, right? So this is case 2 from lesson 4. And we said that the one-sided limits are plus or minus infinity, except, oh wait a second, what's the only type of discontinuity that gives us this? Someone else? Vertical asymptote, good. So we get a vertical asymptote, which I'm just going to abbreviate as VA, at x equals negative 5. Okay. So that takes care of that. So any questions on parts, well, the first part of example 1? Okay, cool. So the next one I want to look at is this piecewise function here. So we have f of x is 7x plus 8 if x is not equal to 9, but 61 if x equals 9. Okay. Now, as we mentioned before, generally we would have to check to make sure each of these pieces of the piecewise function are continuous, but as we see not only in this example, but in the examples to follow, we don't have to worry about that too much. So 7x plus 8 is continuous as a polynomial. So only need to check x equals 9. Okay? So in this case, the only candidate for a discontinuity is going to end up being x equals 9 here. So in this case, if we just have that x is not equal to 9, then we only really need to focus on the two-sided limit here, because in this case, we only really need to focus on values of x that are really close to 9 but not equal to 9. So in this case, the two-sided limit just corresponds to approaching 9 from either direction. So we only need to focus on the two-sided limit here, as we sort of saw in lesson 4 from last time. So if that's the case, the limit as x approaches 9 of f of x is the same thing as the limit as x approaches 9 of what? So remember, for x approaches 9, we just have to make sure we're close to 9, but not equal to 9. So which of the two pieces do you think we'll need to use here?
It's 7x plus 8.
7x plus 8, right? Okay. So then if we just focus on this function here, then, or this limit value here, then what do we end up with as our limit value? 71, right? Because in this case, we can just plug in x equals 9 in here, and nothing bad will happen. So we have 7 times 9 plus 8, which simplifies to 71. On the other hand, though, but what about f of 9? Well, if we just take a look at the definition, well, if x equals 9, then f of x equals, well, 61. But, well, obviously that's not 71. So, if that's the case, that says, all right, our two-sided limit here exists and is finite, but it's not equal to our function value, so what do we end up with as our discontinuity here? Jump?
Probably.
Well, remember, the two-sided limit exists and it's finite. So we want to have a jump, but a hole, right? So a hole at x equals 9. Okay. So that's example 2. So any questions on that? All right. So in example 2, we only really need to look at the two-sided limit because if x was approaching 9 from either direction, but not equal to 9, then we only really need to focus on 7x plus 8. But now in part 3, well, now if you approach x from different directions for our values of 0 and pi over 2, well, you end up with different functions here, so we do have to actually be careful and check the individual one-sided limits here. So, but the nice thing is, again, each of these functions by themselves are continuous, so we only need to check where they meet up. So each piece is continuous, so only need to check x equals 0 and pi over 2 for a potential discontinuity here. Okay. So let's see. Again, let's just focus on the one-sided limits here, and let's start with x equals 0. So let's start with approaching 0 from the left. So if that's the case, then what can we get about the limit as x approaches 0 from the left? So that's the same thing as x approaching 0 of which piece of f of x in this situation? Yep, x squared plus 1, right? Okay. And so the good news is that since this is a case 1 limit, you can just let x equal 0 in here. Then you just straight up get 1 for nothing too crazy here. Okay? Now let's do the same thing with approaching 0 from the right. So limit as x approaches 0 of f of x from the right is the same thing as x approaches 0 from the right of which one? Go ahead. Cosine x. Okay. And the good news is that cosine x is everywhere defined, so we can just let x equal 0 in here to get what value? 1, right? Because remember, we got to use our unit circle here because this is 1 is cosine of 0 here. Okay? So the good news is that so far we got that the one-sided limits agree with each other. So at least the two-sided limit exists and is finite. So let me put that down there. So at least here we're not going to have a jump. So now let's check to see what the function value itself is. So if x is equal to 0, then based on the way our function is defined, it seems like we're going to need to use this top piece here. But, oh, wait a minute, we kind of already found out what x equals 0 is through this part right here, right? Because if we just let x equal 0, well, x squared plus 1 evaluated at 0 is just 1. So that's just 0 squared plus 1, which is f of 0. So the good news is that we have that the limit as x approaches 0 of f of x is just f of 0. So what does that tell us about what happens at x equals 0? Do we actually have a discontinuity there? No. So in this case, we just get continuous at x equals 0. Okay. So that's for 0. Now let's see what happens with pi over 2. So pi over 2, again from the left, f of x. So in this case, if we approach pi over 2 from the left, that's the same thing as approaching pi over 2 from the left of which function?
Cosine x.
Cosine x, good. So in this case, we again have cosine, which is everywhere defined. So it simply suffices to find the cosine of pi over 2, which is what? 1? 0, right. Remember, you got to use our unit circle here. So that's cosine of pi over 2. Okay. So now let's focus on the right side limit now. Pi over 2 from the right of f(x). So limit as x approaches pi over 2 from the right of f of x is the same thing as the limit approaching pi over 2 from the right of which one? Yep, 5 sine of x over, plus 3. So in this case, sine of x is everywhere defined, so we can just evaluate 5 times sine of pi over 2 plus 3, which is just what? Yeah, it's 8, because remember, sine of pi over 2, as per the unit circle, this is just 1. So you have 8 here. But wait a minute. In this case, the one-sided limits exist and are finite, but they don't agree with each other. So that means that the two-sided limit can't exist. So what does that tell you about what kind of discontinuity we get here? That's where we get a jump. Good. Jump at x equals pi over 2. Okay. So that takes care of part 3. So before we do part 4, one remark I want to make here is that, so the way you plug this into on kappa here is that the questions are going to ask you, where are there going to be discontinuities here? So in this case, they only care about, the discontinuities. They don't care if you have a continuous point. We don't care. We're not focusing on that. So in long kappa, there's essentially going to be 4 boxes. So we put there's going to be 4 boxes. So this row here is going to say, okay, we have a discontinuity at here, and here's the type of discontinuity. So in this case, since the only discontinuity you end up with is pi over 2, you say pi divided by 2. So I'm going to zoom in because it's a bit hard to see that, but so pi over 2, and then there's going to be a little drop-down menu, and then you would say pick the choice that says jump. Okay? And since that's the only discontinuity, you would say, okay, this essentially is going to be blank, so to fill that in, you would say does not exist, and then choose does not exist in the drop-down menu for the second option. Okay? So, and if there are 2 types of discontinuity, if there are 2 values of discontinuity, you would put the smaller value of x first. So the smaller value of x goes in this first row here. So if two discontinuities, smaller one, smaller x value in first row. Okay. All right. So any questions on that? All right. So why don't you guys, I'm going to give you guys a few minutes to try example 4 on your own, and we'll reconvene in about 5 minutes. You guys about 1 more minute. Okay, so let's go ahead and reconvene. So So first off, what did you guys get as a result? So I think you had your hand up before, so let's go ahead and ask you what you got.
I got a jump to x equals 0.
Good. So ultimately, we're going to have a jump at x equals 0. Good. So let's go ahead and talk about why that is. So in this case, if we're going to end up having a jump, the first thing we need to do is check. All right. Well, f of x is two completely different functions in each individual direction. So we need to check the one-side limits. So approaching 0 from the left and approaching 0 from the right. So if we're approaching 0 from the left, well, that means that we should be using e to the 2x minus 8, which this is a function that's continuous everywhere. So all we have is e to the 0 minus 8. We just split x equals 0 here. So we should just end up with 1 minus 8, which is negative 7. But on the other hand, for the right side limits, well, if we're approaching 0 from the right, that means we should be focusing on positive values of x. So we should be focusing on 25x plus 7. So again, this is a polynomial that's continuous everywhere. So we have 25, just let x equals 0 here, plus 7. And we just end up with 7 here. So since these one-sided limits exist and are finite, but do not equal each other, well, we should end up with a jump at x equals 0. Okay? Cool. Any questions on that? Alright. So, I forgot to mention this at the start of class, but I'm also going to host Zoom office hours tonight from 6 to 7. So I'll send an email about that shortly after class. So you guys are aware of that option. But otherwise, I will see you guys on Friday. Finally talking about the notion of the derivative.